Good morning, students. Welcome to Commutative Algebra lectures. In this lecture, we'll discuss about a tensor product of modules. Okay, so we have seen already what is meant by module, some of the properties of modules, and so on. So in this lecture, we'll discuss about what is meant by tensor product of modules because we have seen the product of modules may not be defined. So we will see some similar to like product of modules, but it is not product; it is actually tensor product. For that, we all know already from vector space what is meant by bilinear. So whenever you have a map from M cross N to P, where M, N, and P are A modules, okay, these are all three A modules. Then we say that this map is bilinear, means linear in M and if it is linear in N. So what is meant by saying that it is bilinear? If you have trilinear, N linear, and so on. So you fix one coordinate, then it should be linear in the other coordinate, right? So that means f of, if you fix an element here, then this should be linear in M. That means alpha x plus beta y. If you take, it should be same as alpha times f of x comma z plus beta times f of y comma z. Similarly, if you fix some an element in M, then it should be linear in N. That means if you write some alpha times z1 plus beta times z2, it should be same as alpha times f of x comma z1 plus beta times f of x comma z2. Right? This you can n linear also you can define. That means when you are defining for more than 2 or any n, what you have to do is you fix remaining n minus 1 and make sure that it is linear in that particular one. Okay, suppose you have m cross n cross m and 3, then fix 2, then it should be linear in every time you have to check that it is linear with respect to one coordinate, right? Then we say it is n linear, right? Now we'll try to get some concept of tensor product. For that, we'll define this theorem, and in that theorem itself, we'll see how tensor product is defined for given two modules M and N. So take M and N; these are two A modules. Okay. Then, whenever given two modules M and N, then there exists a pair. So there exists a pair T comma G, okay, where T is a module, namely that is the tensor product of M cross N. We'll see how that T look like, okay. And what is this G? This G is a linear bilinear map from M cross N to T, which satisfies something called universal property. What is meant by saying universal property? So if you have any, so what is meant by this universal property? If we have any bilinear map M cross N to P, so we already have one bilinear map M cross N to T, M cross N to T, this is your G. This has a universal property is same as saying that whenever we have a map from M, bilinear map from M cross N to a module P, if this is F, then there exist T to P, okay, there exists T to P, you can call it suppose F prime, such that this diagram commutes. What is meant by this diagram commutes? From M cross N to P, you can go via M cross N to T, then T to P. That means F is same as F prime compose G, right? So you can say that any A bilinear map from M cross N to some module P splits via this T. That is our tensor product. Okay, fine. And not only that, you can also have some isomorphism if T and G and T prime and G prime. If these two satisfies this universal property and so on, then there exists a unique map isomorphism actually from T to T prime, okay, such that this G composed G is same as G prime and so on. Okay. That is from here you can write if G is a map from M cross N to T and G prime is also G prime is a map from M cross N to this T prime. This you have G here and from, so this is G, and if you have T prime, this is G prime, then there exists an isomorphism from T to T prime, okay, satisfying this condition. If you call it this is J, then this diagram completes. Okay, that is the thing. What you have to we have to actually understand here is this universal property we use several times, okay, and sometimes we also use this isomorphism whenever we want to show that two t and t prime, their two modules are isomorphic to each other. Then if we can construct two pairs, okay, satisfying this condition, then they are also isomorphic, okay. So most of the time we use this, okay, and some places we use this technique, right? The construction is not at all difficult one. You take given m and n, take C as a free module. We have seen last class what is meant by free module. A m, this one. Okay, that means if m and n are finite, say suppose, then this m cross n will have that many mn elements and so on. You take n copies of that A, right? That is same as saying that the C is summation ei xi comma yi, where ei's are, this is every time it is a finite sum, okay, from 1 to n you can call it, where ei's are from that ring and xi's are from m and yi's are from n, okay. Remember, you no need to simplify this, it is just an expression, okay, it is an expression and of this form, okay. uh, just like say suppose 2 plus 3, you should not write it as 5, just like this one, okay, is the set of linear combinations of elements of m cross n with coefficients in A. I have given an example here. For example, m is z2, n is z2, then if A is z, then if x belongs to A, m and z, then it can be written in this form, okay, right? So you are not supposed to simply simplify this and write it as one element and so on. That comes later, right? Now D with the submodules of C generated by the following elements. So you take D, which is a submodule of C, such that it is generated by such elements. Okay, so x plus x prime comma y minus x comma y. So it is one element. Okay, and the other element. So such elements you take, and any element combination of these things is an element of D, right? So if you call it, this is like alpha, this is like beta, this is gamma, okay, and this is suppose delta, then any element of D can be written as a1 alpha plus a2 beta a3 gamma, and where ai is belongs to E, okay, that is our D, right? Then you take our T as, because D is a submodule of C, so you take this quotient one, that is our T, okay. So whenever you have something, you can observe that some element is 0 if it belongs to T here, right? So you can check that if x comma y, okay, if you take any basis element x comma y of C, then x, you define this something like tensor x tensor y as x comma y plus D, okay, this is an element of T, right? So if x comma y is in C, then obviously x comma y plus D is in T. That we are denoting this as, if you want, you can say it as a notation, okay, x tensor y, we read it as x tensor y is x comma y belong plus T, right? Now you can see that if C has generators, then this T also has generators, right? Okay, fine. Now one can observe that this D is generated by such elements x plus x prime comma y minus x comma y minus x prime comma y. This belongs to D, so therefore this plus D is same as D. Now you use this one, you can write every time plus D, right? And you take it this to this side, that is same as x plus x prime comma y plus D is same as x comma y plus D and x prime comma y plus D. Okay, right? But therefore this is same as x plus x prime tensor with y equal to x tensor y plus x prime tensor y, right? So therefore this T, elements of T should satisfy, so elements of T should satisfy such property, okay, and D has another three more elements, right? So three more properties we get. So similarly, what are these three properties? The tensor should satisfy three more properties, right? So any T, if you call it as elements of this form, okay, where x belongs to m and y belongs to n, then T should satisfy simply x plus, what is that one, x plus x prime tensor with y is same as x tensor y plus x prime tensor y, or you take here, then it should be same, or if you take a scalar times and so on. Remember, either one place it should come, right? Not ax tensor ay is not same as a time a of x tensor, right? Okay, so only from any one you can bring it outside. Of course, if you bring it both, then it should be something like a b or a square, like that, right? Then this is the main T elements of the mainly call it as a tensor product of two modules M and N, which satisfies these four conditions. Based on that, you get that G and all. So now G, defining G, what we want to define from M cross N to T. Obviously, how you can define any x comma y, simply define as x tensor y, right? Then you can check that it is a bilinear. That I will leave it. It is not at all difficult one. Using these properties, whatever we have here, it is directly bilinear, right? And what we want to show is that if you have, it satisfies universal property. That means if M cross N to P is a bilinear map, then we want to show that there is a map from T to P, that map composed and so on, right? So this from M, if you have from M cross N to P, you will can get it indices a map, or you can extend that F to F tilde from C to P. What is C? Is a free module generated by M cross N, right? So therefore, we can obviously, how we can define F tilde of summation ei xi comma yi, because any element look like here, and F is evaluated at xi comma, so simply you write this as summation ei f of xi comma yi. Okay, then we can make sure that it belongs to P and so on, right? And you can check that F tilde of x plus xy satisfies this and so on, right? So this value is 0, so F tilde vanishes on T. So one can easily check, claim is that F tilde is 0 on this T. That means if you take any element of this form, then using the fact that F is bilinear, you actually get it is 0, right? Okay, so F tilde values on 0. That means this F tilde induces a map F prime, you can call it from T to P, because T is what? T is C upon D, right? How you can define F tilde of any element is x tensor y, you simply define this as F tilde of x comma y, right? But that is same as f of x comma y, right? That shows that this f of x comma y is f tilde of x cross y, but x cross y is g of x comma y. So you got f is equal to f prime composed g. So that map what we are talking about this. And you can check that f prime is unique. It is not a problem because f double prime and f prime, they agree on this basis element, so they agree on whole and so, right? So what is important is how this T is constructed and how elements look like. This you can simply define M tensor N is simply X tensor Y, where X belongs to M and Y belongs to M. And what this property satisfies? If you take X plus X prime tensor with Y, this is same as X tensor Y plus X prime tensor Y, and another one, and AX tensor Y is same as A of X tensor Y, which is same as X tensor A. Okay, basically they should satisfy these properties, right? And M tensor N is actually a module, and we always have a map from M cross, so let me write that properly, M cross N to T, that is M tensor N, which is a bilinear map which has universal property. So this has a universal property. Okay, that means whenever you have a map from M cross N to some P, then there exists a map from here to here, right? Fine. So this universal property actually we use to show that some tensor products are isomorphic and so on. For example, you want to, you know that there exists a map from here to here, right? So if we want to define if you want to define a map from tensor product to something, make sure that you are defining from M cross N to that, ensure that it is a bilinear map and it satisfies universal property and so on, right? Okay, so that we will see here. Some corollary and all, you can go through it. We'll see some of the properties of this modules, isomorphism and so on. So take M, N and P, they are all a module. Okay, then there exists unique isomorphism. The obvious first one is M tensor N is actually isomorphic to N tensor M, right? And the second one is like associative property. M tensor N, then you tensor with P is same as you tensor with N and P, then you tensor with M is same as M tensor N tensor P. So it is tensor product of This is the right hand side. What we have here is tensor product of three modules m, n and p. Okay, so that means there exists a trilinear map satisfying that condition and so on, universal property. Okay, and the next one is you take direct sum of two modules, then you tensor with it. It is same as you take tensor product of mp and np, then you take the direct sum. Okay, and the other one is, if you m is an a module, so if you tensor with a, what you won't get anything, you get simply m itself, right? Okay, so we can see the quickly how this maps, how we are approaching this, remaining all places, checking some bilinearity, all those things. Basic result, I mean, it is not at all difficult. We want to define a map. We show that m tensor n is isomorphic to n tensor n, right? So what we do is we show that there exists a map from m tensor n to n tensor m. Suppose call it this is f. Okay, and we also get a map from n tensor m to m tensor m. Then show that f composed g is g composed f is identity wherever they are defined. Okay, right? Then they are actually isomorphic, right? Now why we can show easily in this way is, this is a tensor product, right? So this is just like our p in that universal, whatever we are talking about, that universal property what we said. Okay, so if we want to get some map from here to here, so it is enough if we show that there exists a map from, so you try to define m cross n to this n tensor m, then show that it is bilinear. Okay, then by using that universal property, there exists always a map from this. This is our p, uh, not this one, this is not our p, this is our p. Okay, so if we have some m cross n to n tensor m, which is p, a bilinear map, then definitely, so if we have this, then by that universal property we have a map here, right? N tensor m to, so what is our p here is n tensor m, right? Is this clear? So what is important is this much part. So try to define a map f, try to define a map f from m cross n to n tensor m, and show that this is a bilinear. If we can show that, define something and show that it is bilinear, then definitely we get a map from n tensor m to n cross m, n tensor. Okay, uh, yeah, so this is our, you can take, this is our n cross m. So you define a map from m cross n to n tensor m, that is here, right? Then we have here m tensor n, we already have, right? Tensor product of this. Then we have a map from m tensor n to n tensor n, right? Then now defining this map is not at all difficult one. How we can define this map? We want to define f maps from m cross n to n tensor p. Simply f of, you take x or small m comma n, simply you define n tensor m. They are all natural maps, and show that it is bilinear, and it is clearly bilinear because what you have right side satisfies by the definition of tensor product elements, right? So this is a bilinear. So therefore, and we already have a map from that g, whatever we are calling it as m cross n. So we already have g, which is m cross n to its tensor, which is m tensor n. That is our t, right? This g we have, and just now we got from n tensor m. So therefore, there exists a unique map from m cross n to m tensor n to n tensor m. Similarly, you can define a map from n tensor m to m tensor n, then show that they are inverse to each other. That is what we have shown here. Okay, right? So I'll skip those things. You can easily check that you got their composition is identity. So therefore, m tensor is n tensor. Only simple thing one should understand is what map we want to define. That is most important thing. Okay, fine. Now the second one is associativity. So what we will show is m tensor n, then tensor with p, we show that it is isomorphic to this m tensor n tensor p, tensor product of three modules. Okay, so this we do in two steps. We directly don't define from here to here. What we'll show is we'll define, you take any z in p, You fix some z in P. Then from M tensor, we will get a map from M tensor n to here. How we do that? To get some tensor and domain, first you define only on Cartesian product. So M cross n to M tensor n tensor P. Suppose you call it this is Fz. How one can define? Fz of any M comma n is M tensor n tensor z. Right? Okay. You take x, y or m n whatever, no problem. Then show that this is actually this map, whatever we are calling it here, show that the exercise or claim show that this Fz is bilinear. Bilinear. That means it is linear in M as well as linear in N. Then how we use that universal property? So we have this M, right? This M uh, cross N to M tensor N. We already have which has a universal property, right? And just now what we have shown is that this Fz is a map from M cross N to M tensor N tensor P, right? So therefore, by using that universal property, what we know? There exists a unique map from, so if you want, you can use another color. So therefore, there exists a unique map from M tensor N to M tensor N tensor P, right? That we are denoting as Fz prime, sorry, Fz prime. That we denote by Fz prime, which is a map from M tensor N to M tensor N tensor P. So for every Z, we are actually getting one map here. Now we define this F maps from, this is one module, okay. Then cross product with this another one to M tensor N tensor P. Okay, if we show that it is bilinear, then again you get a tensor from here to here, right? How we can define this one? F of any M comma N, right? This is M tensor N, sorry, M tensor N, then comma Z is same as M tensor N tensor Z. Or if you want, you put it M F Z of that one, right? It is same F Z prime of this. Finally this, and show that now, show that this F is linear, bilinear, okay, linear in M tensor N and P. So therefore it will become bilinear and you will get a map, right? So finally that is showing is not at all difficult. So you get F is bilinear and hence there exists a linear map, this M tensor N, then tensor with P2 here, right? Okay. Now to show the other way, what we want to get some map, you can call it G prime or whatever. We want to get M tensor N tensor P to M tensor N, then tensor with. So obviously how we can do? Because this domain has all tensors. So obviously you define a G map from M cross N cross P to the same thing. Okay. Then you will get, obviously we will, if we show that this is trilinear, G is trilinear, then we get a map from here to here, right? That is the idea. So every time we are maximum in this proof, we are trying to use that universal, using that universal property, right? So in your domain and codomain, how will they look like, by based on that we can check, right? Simply you take this one, it is not at all difficult one, M can P, you simply send it to M tensor N tensor P, show that this, so G is trilinear, show that this G is trilinear, okay. Then therefore by using universal property you get a map from M tensor N tensor P to, right, here, okay. When you are doing, you can do it like this, so it's not a problem, okay. So therefore we get a unique map, it is this one, and show that they are inverse to each other. That is not at all difficult one, you can go through it, this proof which I have given, right? The most important thing is how we define a map, how we are approaching, that is the thing here. Remaining all are just verification whether they are bilinear or trilinear and so on, okay. That proves the second one. The third one is little different than the previous two, or even the next one which we will show. We want to show that this M, if you go here, M direct sum N, then tensor with P, okay. M direct sum N, then tensor with P, okay. Where is that? Here, M, then direct sum N, then tensor with P, we want to show that it is actually isomorphic to M tensor P, then direct sum with N tensor P. We want to show this, right? So one way we can get it, because if we want to get a map F prime, say suppose M, this you just simply call it, this is something like, for just for understanding, you simply call it, this is something like M prime. So we want to get a map from, we want to get a map from M prime tensor P to something, okay, right? So if, how we can define, you define this, then show that it is bilinear, right? Then you will have a, from here to the tensor, right? That is the idea. So one way we can define, that is M direct sum N, we want to get some tensor, so take Cartesian product. Okay, so obviously what is this map? If you take M comma N, then P, simply define M tensor P, then N tensor, show that this F is, F is, because this is one module, remember, okay, it is Cartesian product of two modules, so show that F is bilinear. Okay, that means linear in M prime and linear in P, where M prime is M direct sum N. Okay, once we show that, so this is a basic calculation that I'll skip. Showing bilinear and all, it is not a difficult one. So F is bilinear. Then here we cannot, is the right hand side, what we are having is not the tensor product. If at all we might have here a tensor product, then from the tensor to tensor we get it, right? So what we do is we use the isomorphism trick here. Okay, so isomorphism trick means we now show that F has universal property. Okay, so that means what is meant by saying that F has universal property? So we have F, this F is a map from, where is F is defined from M, this direct sum N, okay, then cross P to M tensor P, direct sum with N tensor P. So this is our F, and we know it is bilinear. Okay, we'll show that it has a universal property. That means whenever you have a H, whenever we have a H from this M direct sum N, okay, cross P to some Q, okay, which is bilinear, then there exists a map, unique map from here to here, right? Okay, okay. So how we define this H is, we'll define, there exists, we have to prove that there exists some G such that H is equal to G composed. So how we'll define this G? We'll define in using two maps, G1 and G2. So we'll define G1 map from M cross P to Q, okay, and then G2, G1 and G2 will define in terms of H. How we can define G1 of M comma P, this is H of, we should get an element of this one. So simply you can write as M comma 0, then P. Similarly, G2 you define, which is from N cross P to Q, G2 of any N comma P, or whatever you write, P, P prime, no problem. It is, this is same as H of, this time you don't have any elements, so 0 comma N, then P. So that G1 and G2 they are bilinear and so on. So therefore, by showing that G1 is bilinear, there exists a unique map G1 prime from M tensor P to Q. This is possible, right? Similarly, so G1 prime we have from M tensor P to Q. Similarly, G2 prime is also mapped from M, this N tensor P to Q. Okay, so therefore you can define G. Now we get G1 G2, so therefore we can get a define a map G from M tensor P, okay, direct sum with N tensor P to that Q. How we can define G of, if you call it this as some element T1 and element T2, T1 comma T2, then this is simply G1 prime of T1 plus G2 prime of T2. Using G1 prime and G2 prime, we can define this. Then there are an element of Q, you can check that. Now show that this G is a linear map. Okay, linear map. It is not something like bilinear and so on. This G is a linear map we want to show, right? So it is not at all difficult one. You can check that. and also show that H is equal to G composed F. So therefore this F satisfies universal property. So F has a universal property, right, from M direct sum n, okay, cross P to this M tensor P direct sum n tensor P. This has a universal property, and we also have such another map which also has universal property. So therefore those two will be isomorphic. And what is that one? The natural tensor map from M direct sum n cross P to M direct sum n, then tensor P. Obviously we have this one. This is a natural tensor product, right? Simply this is one module, this is another module, so therefore you have tensor product of those two modules, right? That is simply tensor map. We can call it as a natural tensor map. Okay, so if you remember, G comma T and G prime comma T prime, whenever you have such two pairs, when we constructed the tensor product, then there exists a unique, right, map from T to T prime. See, G and G prime both should satisfy universal property. Then what we know is that T is isomorphic to T prime. T is isomorphic to T prime. So we use this one, that if we want to show that two modules are isomorphic, make sure that you have a bilinear map G comma T and G prime comma T prime. G and G prime satisfies universal properties. Then T is isomorphic to T prime. Now what are all we have here? This F is a bilinear map, and we have M tensor P direct sum with n tensor P. Okay, this is one pair, and what is another pair? Is this tensor, natural tensor map, and M direct sum n tensor with P. Okay, this F and this both satisfies universal property, therefore these two are isomorphic. Okay, that means we have proved that M direct sum n tensor P is isomorphic to M tensor P direct sum with n tensor P. Okay, so it is little trickier than the previous one too. Okay, so you can see that what we have explained here, I have given this proof. And the last one is, we want to show that A tensor M over, of course, A is isomorphic to M itself, right? That is obvious. You can define from A cross M to M. You want to get A tensor M, right? So you define simply A cross M to M. F of A comma M is AM, then F is bilinear and so on. So there exists a map from A tensor M to M. Similarly, we want to get a map from M to A tensor M, right? Okay, so that you can G prime, which is directly you can define simply G prime of any M. G prime of any M is, because a ring we know it is commutative, so you simply write as one tensor M, and show that this, whatever you are inverse to each other, so you get this A. This is not at all difficult, right? Fine. So now let's see some properties. If we have F maps from M to M prime, okay, and G from N to N prime, these are two module homomorphisms, then we can define H, this M cross N, H from M cross N to M prime tensor N prime. Directly we can define H of M comma N as this, you call it F of M, this F of M tensor with this G of N. Okay, and you can show that this is simply H of this one, right? This H is bilinear, so therefore you get a map from, there exists a unique map from this M tensor N to M prime tensor N prime. So you have a map from M cross N to this, which is bilinear, right? So therefore that universal property you will have from M tensor N to this, you can call it this as F tensor G. So whenever you have F and G modulo homomorphisms, then you have a tensor, you can call it tensor modulo homomorphism F tensor G, M tensor N to M prime tensor N prime. Simply this is how it is given. So F tensor G of any M tensor N is what? F of M tensor with G of N, right? Also, composition also you can talk about. F prime is a map from M prime to M double prime. So if you have M prime to M double prime, if you have this n prime to n double prime, this is f prime, this is g prime, then you can talk about f composed f prime and g composed g prime. Okay, then you can also talk about their tensors. It is same as composition of tensors. These are all one can easily check, right? These are the properties of tensor, how we have defined a tensor product, and what are the properties we have seen. I can quickly explain. If you take m and n are two modules, okay, a modules over a, then m tensor n is nothing but how it is constructed: x tensor y, where x is in m and y is in n. They satisfies those particular four conditions, namely x tensor y plus y prime is x tensor y plus x tensor y prime. Okay, other one is ax tensor y is a into x tensor y. Okay, basically these two, there are two other versions of similar type, right? So, and uh, the how we are actually using is this, that m cross n to m tensor n, there exists a bilinear, there exists actually a unique bilinear map. Okay, so whenever, and it has universal property. So whenever you have something like p here, if we have that, call it suppose f, if this f is bilinear, then there exists a map from tensor of m and n to here, right? So this we have used several times in proving the above result. Okay, so we'll stop here. In next class we will talk about some other properties.